All right, good morning, everyone. And I promise you we will be done a little early today. I am not holding my class tomorrow, so today we have only an hour or so. All right. You do still have the full week after break to ask any questions about your exam. So if you didn't bring it with you, haven't had a chance to look it over yet, please do so. You have to do that before March 11th. That's just so that we can have that deadline set. We can't be having you after your grades are determined at the end of the term, trying to argue back a point or something like that. Look at it now. It's for your benefit. Homework 4 course will close out today at 5 o'clock. My next slide is going to be a little overview, and there'll be a couple homework 5 helps along that overview. That goes up. Actually, it's already up this morning. That's not due till the Thursday after break, but you will be able to try any questions out after today's lecture. It's all about the mean. So those are my primary announcements. Do you have a question or comment at all before we turn to that overview? All right, you may sit back and listen. You could take some notes on the back of one of those pages where it has a spot to take notes, like page 138. At the end of any section, there's always a blank spot there. I'm going to highlight how we've been working through learning about a population mean, with a couple of homework 5 notes along the way. Oops. We have, if I could have your attention, please. We have made our way through 3 parameters so far. And your exam 2 in March, end of March, will be over the 5 parameters as a whole. We have covered proportion P, how to estimate it with a confidence interval, how to test hypotheses about P. That was even on exam 1. Your homework that's being turned in today is about 2 proportions. So there's 2 populations or 2 baskets. But the response that you're measuring is still one of those yes-no kind of questions. You're recording successes and failures. But now you're comparing 2 proportions, P1 and P2. We turned then to learning about a population mean. We're back to 1 population of interest, but what we're measuring isn't yes and no's for answers. It is a quantitative response. And we're wanting to learn about the true mean response, the average time, the mean score. So we've learned how to do that through a couple of processes. We have 1 population. Our response X is a quantitative response. We're interested in learning about what the true mean for this population might be. We don't have the ability to look at every person's response in that population to get the true mean or average. So we go to that population and we take out what we hope is a representative sample, a random sample of some certain size n. And since now we're trying to learn about the mean of a population, the natural thing to do with the data that we have coming from that population would calculate the mean of that sample. And that mean of the sample, we have notation for. We would calculate the sample mean, called X bar. Sample mean X bar would be our estimate of that population mean mu. It is our statistic that we use to estimate that true mean. And there's our process. We know that if we repeated that process, go back and take another random sample, calculate that X bar, it's likely to be a different answer. And if I were to continue doing that process, I would start to see all the different values that the X bar could take on. And you studied in your labs this week what kind of model X bar has. What kind of values could the sample mean take on? What kind of model would it be? You found out it would be either approximately or exactly normally distributed. Around what quantity? Around the true mean mu. So we learned about the model for X bar. We learned that if we were to repeat this process, getting all those values of X bar, we learned that X bar is either going to be approximately or exactly normally distributed, centered at the true mean mu, so it's an unbiased estimator. And then there was that new standard deviation that showed us that averages, X bars, vary less than individual values would. Gets divided by the square root of n. It is this model for X bar that you need to use for questions 1, 2, and I believe 3. On homework 5. The first 3 questions are from chapter 9, learning about the model for the sample mean and how it varies. In 2 of those questions, the first 2, you're given, let's consider the population of all salaries. The mean salary is blank, and the standard deviation is blank. You've got the population information. You've got mu and sigma known. And then you're asked to talk about what kind of values would you expect a sample mean coming from that population to take on. So you're going to be able to draw that normal model and use that model to find a probability, perhaps. It's very similar to the ACT score example we did back in chapter 9, a few pages back. So keep that one in mind. Because what I have students doing is we have done some confidence intervals, and we're going to do some more testing today, and we're into those T's. We're doing T star values. We're doing a T statistic. So they think that as soon as you hit means, it's got to be a T. T's are used for doing the inference side. When we make a confidence interval or doing a test, we have to work with the T distribution. But it comes from still this normal approximation that we have for the sample mean. The sample mean will have a normal model, and if we know mu and sigma, we can put in the values to figure out exactly that normal model. You have that information in these first few questions because that's what it's talking about, trying to learn about what X bar could take on for values. But as soon as you move to the testing or confidence interval side, the whole issue is we don't know mu. We don't know sigma. And so when we get to the confidence interval or testing, we have to put in the S. And it's a putting in of that S instead of sigma that makes us move to a T distribution that we have to work with. So questions 1, 2, and 3 are about chapter 9 results. They're about either the central limit theorem, which is that approximate result, because you have a large sample size, or it'll be based on just the exact result, since you were told you have a normal model to begin with. When we move to the inference side, which are the remaining questions on homework 5, confidence interval or hypothesis testing. On the confidence interval side, what do? We took our best guess, which is X bar, but because we know it would vary from sample to sample, we're going to go around that best guess, reflecting that kind of variability. So we have a range of values that we are pretty confident about. We always go out a few standard errors. And it is that standard error of X bar, S over square root of n, that makes that multiplier next to it become a T star instead of a Z star. Do you remember the conditions that you have to have met in order to do something about proportions, to get to a Z? You need to have a random sample always, but your sample size needed to be large. And you had to check that at least 10 rule for your different situations. When we're doing tests or confidence intervals for means, we don't say you have to have a large sample size. We just say you have to take a random sample from a population that over here has a normal model. A normal model for that population. That normal model for the population condition could be relaxed a little bit if you do take a large enough sample size, because then you'll get to this nice normal result for X bar by the CLT instead. But it doesn't require that you take a large sample size. And for that reason, when you use S instead of sigma in your standard error here, you have to reflect that a little extra variability that can happen with that t-star multiplier instead. We learned that the t-star multiplier we look up in our table, that if you had a really large sample size, it becomes practically a z-star anyway, but it does have to be the t to reflect the right distribution. The same ideas for interpreting the confidence interval and interpreting the level of confidence pertain to this one too. Just make sure you adjust for talking about a mean instead of a proportion. And you have a couple questions on that. And then the hypothesis testing side is what we've been doing more recently. If you were writing out your H0 and HA, and we're trying to learn about the population mean, our theories about the population, in particular the value for that mean. We will have a null hypothesis, a status quo, that the true mean is some specified value. Our alternative might be a certain direction, greater than, less than, or not equal to that value. And our test statistic will take the sample mean, let's suppose this value is 20, and subtract that null value, see how close we are to H0, and we'll see how close we are in terms of standard error units. It starts to look like you would call this a z, but when you put down here the standard error and not the standard deviation, this becomes a t. It follows a t distribution. Now on those first three questions, Q1, 2, and 3, you have sigma known. It's given in the problem for those first two questions. So when you have to find a probability under that normal curve, you'll be able to put sigma down here and actually find a z-score, like you did on the ACT score example in our notes. But if you're doing a hypothesis test, all you have is a sample. You don't have the true mean, only a hypothesized mean. You won't have the true standard deviation, so you're going to have to put in the S. And that's why we calculate a t test statistic when doing that test. We learned a little bit about how to work with a table to find p-values for our t statistics. And once you get the p-value, though, you make this decision the same way. You reject H0 if your p-value is too small, less than or equal to alpha. So what we have today is one more hypothesis test example, and then seeing a little connection between these two inference ideas, how you can use a confidence interval to do a test, and how that link is made. And then one more last good example, that's an example from an old exam that we'll get through. So I think we're at page 130 for our notes. Where we have a second example. Right, we finished page 129 together? Okay. So page 129, we did a full t-test ourselves, by hand. On page 130, we're starting to see some output. Talking about calcium levels. A bone health study looking at daily intake of calcium for women. They're concerned that the mean calcium intake for the population of all such women is not meeting that 1,200 milligram level, as it should. They think that the population mean might be less than that 1,200 milligram level. When you read the question, you start asking yourselves, how many populations am I looking at here? One population of all women. What am I measuring? Calcium level, quantitative. And I see the word mean in a couple different places. One of the biggest problems for exam 2 will be reading the scenario and understanding which of those 5 scenarios or parameters we're talking about. And there's clues. What are you measuring? Calcium level. Does it say something about a mean or a proportion in there or a rate? It's talking about a mean. And in this case, we're talking about, is the population mean less than 1,200 milligrams? We want to perform that test with the data from these 38 women. So the first step is to write out the hypotheses. Let's let mu represent that population mean, calcium intake for all such women. The status quo would be that they are meeting their daily requirements, that the true mean is either 1,200 milligrams or larger, because the theory that's stated right here is that the population mean, they think it's less than 1,200 milligrams. The alternative hypothesis has that specific direction that they're looking for. The equal is always in H naught. You can write H naught as greater than or equal to if you wish, but we'll be looking at our data compared to 1200. So there's the hypotheses. You might be asked occasionally to identify that parameter. And if you're identifying mu, you should always write out what phrase first. It is the population mean. You can always say it is the mean calcium intake for all such women. But if you say population mean, then I know directly you know it's a population mean. That word is right there. All right. We have some data. Let's take a look at what happened when they measured these 38 women. They have the sample size of 38. And there is the summary statistics. The mean was 926. Does that look like it's less than 1200? Mm-hmm. And we'll see how much less, not just in terms of difference in milligrams, but in standard error units. The standard deviation is provided for us, so we wouldn't have to calculate that with our calculator by hand. There's the S. And that number right there is pretty big. That tells me that the individual women had quite a range of values. They varied a bit. They varied around 926 with a give or take of 400 some. Individuals vary quite a bit, but this number here, that's 69.31, is your standard error of the mean. Sometimes it's abbreviated SEM. It's your S over the square root of n already computed for you. That reflects how a sample mean varies. It's the standard error of X bar, the sample mean. So one of the things we're first trying to do here is to interpret that number, which is much smaller than the individual standard deviation. So the standard error of X bar turned out to be 69.31. Well, first of all, I know that the standard error is estimating the standard deviation. It's estimating that sigma over square root of n. So let's start out with that phrase. We estimate. And then we think of a standard deviation as an average distance. We estimate the average distance of what? Average distance should be distances of values from some frame of reference. Average distance of these values from their mean. Well, what values are we talking about? It's a standard error of X bar, so it's the X bar values. We estimate the average distance of the possible X bar values and we want to take that and look at that distance from their mean. What's the mean of the X bar values again? That was mu, the true mean. So it's going to estimate the average distance of these possible X bar values from the population mean mu. We estimate the average distance of those X bar values from mu to be about how much? 69.31 milligrams. To be roughly that far away from that true mean mu on average. So I've got the average part, I've got that there's more than one value, and I'm talking about the X bar values. I've got the frame of reference, how far away are they from mu. And it's not exactly that average distance, so we put in that about or roughly. Averages don't vary as much. An X bar value based on 38 women would only tend to vary from this true mean mu by about 69 milligrams. That's how accurate this kind of an X bar would tend to be. All right, the next part of the output that you see is performing the test for you. You're going to be asked to provide the null value, because in order to do your test of H naught mu is 1200, it's got to know that's what I should compare my data to. So one of the options when you pull up the dialog box is to put in the null value when you're learning about a mean. So you enter that 1200, and then it conducts the test for you. This is the part that is doing the test here. The t-statistic. We don't have to compute it, although we could from our summary measures, but it is already calculated for us to be negative 3.953. It would be found from taking your x bar of 926, subtracting off the hypothesized or null value. And the bottom again is that standard error. You're asked to interpret that number, negative 3.9, as a difference from the hypothesized mean. What does it mean? Negative 3.9. Our sample mean is almost 4 standard errors below 1200, right? If your t-statistic is negative 3.9, almost negative 4, then how far away was x bar from this 1200? Nearly 4 standard errors below, because it was negative. Our sample mean was nearly 4 standard errors, not standard deviations, but standard errors, in this case below that hypothesized mean of 1200. That's pretty far away. I mean, I knew 926 looked really small compared to 1200, but how small was it? Well, it sits almost 4 standard errors below 1200. That's quite a few of those average distances. So do you think you're going to be kind of extreme? Have a pretty small p-value? And indeed we will. We have the t-statistic, so just be careful that when you have output provided, you don't start recalculating things that are already there given to you. Sometimes I'll have the data in a column so you can see the data, or maybe a graph of it. The summary measures come out by default, but you don't have to recompute the t for me. It is already provided there. Now, the degrees of freedom of 37, does that make sense? Because there were 38 women, n minus 1. And then there's this thing next to it called SIG, two-tailed. SIG stands for observed significance, also known as your p-value. It's what you compare to your set significance level for doing the test, what you observe through the data, the p-value. And it's also for a two-tailed test. So we're going to have to adjust that to do our one-sided test. Let's draw a picture of what that p-value looks like. If you're doing a t-test, you're going to draw a t-distribution with a certain degrees of freedom. In this case, we have 37. The test statistic that we observed was negative 3.9, way down here. And our p-value, again, has the same definition. Find the probability of getting what you observed for your test statistic, or something that's even more extreme than that, under this H0 model. More extreme, you look at your HA. Our HA is to the left. So I really do want just this one small tail area. That is our p-value. But SPSS, when it does the test for you, it doesn't know if you're doing a one-sided test or a two-sided test, or what direction you might be looking for. So it's going to, by default, give you the two-sided p-value, which means it'll take the test statistic that came up and the opposite one and give you those two tails. So this 0033 is the two tails together, but we just want one of them. So how do we find our p-value? Cut it in half. Our p-value is going to be 0.0033 cut in half. Very small. Now, if we were doing this test one-sided like we are, and our test statistic did not turn out to be negative 3.9, but rather positive 3.9. Just suppose we actually came out to be more than 1200. The two-sided p-value in SPSS would be the same, because it would have taken the positive number and the negative one and found those two tails. But if we were really over here, and we were doing a low or a lower tailed test, what would be our p-value? We would do as extreme or more extreme, and it would be cutting that in half and then doing 1 minus. So you just have to draw the picture, and you'll make sure you do the right thing. It's not going to be always just cutting that two-sided one in half, but probably 99% of the time it will be. There's a very good bright yellow supplement. I think it's supplement number 5 or 6 in the front of your lab workbook. Completely explains SPSS's two-sided p-values and how you adjust them to do a one-sided test, and kind of just goes through those different examples. Our p-value, extremely small, right? So what is our decision? We will reject H0. What would be our conclusion? We are able to support that alternative theory. We're able to reject H0. The alternative theory said something about the population mean. We would have enough evidence to say the population mean calcium intake is less than 1,200 milligrams. This is, of course, for the population of women that our sample represents. There is sufficient evidence to say the population mean calcium intake is less than 1,200 milligrams, that recommended daily amount. You can always add the idea of for the population represented by your sample, because that's really all you can infer your results to. If all of these women were over 40, you really couldn't talk about women that are under 40 for this theory applying to. But you have to have the indication of the population mean, or we would say that women in general are not meeting their recommended daily allowance on average, because it's not for every woman, it's the average. All right, we have a clicker question here in the middle, and then there'll be 2 towards the end. So I added a part F, if you will. So we just rejected H0. We decided to support that the population mean was less than 1,200. And the clicker question has to do with the fact that we made a decision. What type of statistical error could have been made? Those definitions of a type 1 and type 2 error. Make sure we don't get those mixed up. What did we decide? We decided to reject H0. Now, obviously, most researchers like to think they are very smart. But in any hypothesis test, it's either right or wrong. All right, you're doing pretty well, except for someone who chose E. It's always the case. Let's take a look. Indeed, a type 1 error, right? Type 1 error is made when you reject H0, but H0 was really true. Now, if I asked you, what is the probability that the researcher made a type 1 error, what would your answer to that have to be? Alpha represents the probability of a type 1 mistake, but you can only talk about alpha being that probability before you've made the decision. The process we use does guarantee that if you were to repeat it many times, and H0 really were true, you would make a type 1 error 5% of the time, if that's your level alpha. But every time you make the decision, it's either right or wrong. So what's the probability that this researcher made a mistake? It's either 0 or 1. They either did not make a mistake or they did. If H0 is true, the process we use is guaranteeing that a type 1 error would happen no more than 5% of the time. But every time you do the decision-making process, it's either right or wrong. You either reject H0 or you don't. Good. We make sure that we don't make mistakes very often by using these methods that guarantee those rates are pretty small. All right. Section 13.5 has a nice connection for us between confidence intervals and testing. Let's suppose we just made a 95% confidence interval to estimate a population mean. And our range of reasonable values is going from 60 to 70. Maybe this is on an exam or something. 60 to 70 points is our estimate of the range for the true mean. So would you say that the true mean could be equal to 68? Would you say that's a reasonable value, an acceptable value? How about the true mean? Do you think it could be 72 or 58? Anything that's inside the interval is a value that we would have to deem reasonable, plausible. A value for which, if we were testing H0, could the mean be equal to 68, we would have to say, yeah, we couldn't refute that statement. 68 is in that interval, so we could not refute the true mean being 68. Whereas if we were testing that the true mean is equal to 72, we would say, no, we'd reject that theory. Because according to our interval of reasonable values, it's not a reasonable one. It falls outside. Any null value that's in the interval, we would have to stay with that null value. We could not refute it. Any null or hypothesized value that's not in the interval, we would be able to reject. And there's that one-to-one connection. Your confidence interval is kind of giving you this range of values for which you would stay with H0 versus reject H0. In the following sense, the alternative hypothesis needs to be two-sided for this to match up exactly. If your alternative hypothesis is not two-sided, like you saw in your homework 4, sometimes the conclusion from the test can be different than the conclusion from the confidence interval. Because the confidence interval is knocking out values on both sides, whereas if you're doing a one-sided test, you're putting all of your, let's look to see if we can reject, on one direction. And you might be more likely to reject there. There's also the need for the significance level to match up in some sense with that confidence level. Do the test at 5% to match with your confidence interval results at 95%. But we will be able to reason through how to adjust that in some cases. There are such things as one-sided confidence intervals, which we aren't going to go through, but you can work that out too. And then the last comment is simply that for means, the relationship holds exactly, because it's the same standard error in the confidence interval, s over square root of n, as it is in the test. For proportions, do you remember when you'd calculate your statistic for a proportion? You put p naught, 1 minus p naught in the denominator. But when you did the confidence interval, you put in p hat. So the standard errors are a little off. But we'll still have it hold approximately. So we're going to try it out. Let's see if we can reason this idea through by looking at a confidence interval that estimates the mean time for teenagers spending watching TV. 95% confidence interval for the mean. 2.6 hours is the best guess. That was the sample mean. What would be the name for this 2.1 that we're going out plus or minus? That's your margin of error. That is your t star times your standard error put together. And there's our interval from a half an hour up to not quite 5 hours, 4.7. So we have 4 sets of hypotheses. They're all two-sided, so we'll be able to make the connections. We have to decide whether we can reject H0, we can't reject, or maybe there's not enough information to be able to make that decision. So I'm going to do the first one with you and then have you try out the other 3. The first one, null hypothesis. Is the true mean 5, or would we refute that and say it's not 5? The significance level indeed matches with our 95% level of confidence. So we simply have to do what? Is 5 reasonable or not? Look at our interval. 5 is not in the interval. It's not a reasonable value. So our decision here of this hypothesis test would be to reject H0. Our reason is very simple. Since the value of 5 is not in the 95% confidence interval for what we think mu could be. We don't have to do a t statistic. We don't have to draw a t distribution and find some p-value. We know the decision. In fact, since we know we would reject H0, tell me what you know about the p-value. Since we know we rejected h naught, what do you know about the p-value? It's small. How small for sure? Less than or equal to 5%. Good. Good. All right, I know you can do B. It's just got a different hypothesized value. Same level alpha, 5%. And then I want you to try to think through with your neighbors C and D. What's different in C and D is that you have a different level alpha. So you can either think about what the confidence interval will be doing if you change your confidence level, wider or narrower, or you might be able to reason it through from the p-value idea. But I'll give you about 2 minutes to try out B, C, and D, and we'll go through them together. And then we've got one last question on page 133. So try them out. Chat a little bit. Check with your neighbor. All right, let's try them out. Part B is a straightforward application. Again, you're asked to do a test at a 5% level using your 95% confidence interval. Different hypothesized value now, it's 4. And 4 happens to be not the middle, but still in your confidence interval. It's a reasonable value. So you know your decision for this hypothesis will be what? Fail to reject H naught. What's your reason why? Since the value of 4 is in the 95% confidence interval. It is deemed a reasonable value, a value you could not refute. That would be true for any number in your interval. If you failed to reject H naught, what do you know about your p-value now? It wasn't small, it was large. Bigger than 0.05 for sure. How much larger, I don't know, but at least it's bigger than 0.05. All right. When we move to parts C and D, It's the level alpha that changes. It's still the number 4, and we've already established the number 4 is in that interval at a 95% level. So if we change alpha to be 1%, we could think about then we should really look at a 99% confidence interval. And what do you know about a 99% interval compared to the 95% one that sits there? It's wider. 4 is already in the interval, and if you're going to make your interval wider because you're going to be 99% confident, 4 is still going to be in that interval. So you know that the answer will be fail to reject H0, but your reasoning has to be a little bit more. You have to say that we know that 4 will still be in the wider 99% confidence interval for mu. You don't have to compute the interval. In fact, you don't have even enough information to be able to actually get that interval. But you know it's going to be wider because that t-star multiplier will be bigger. 95% in the middle, 99% has to go out. And if 4 is already in the interval, it's going to be still in that wider 99% interval. Could you have reasoned it from the p-value idea too? What did you tell me just a minute ago about the p-value in part B? That it would be big? If your p-value is bigger than 5%, how does it compare to 1%? It's still bigger. If your p-value is more than 0.05, then how does it sit relative to 0.01? It's still larger, so you're going to still fail to reject. Your p-value is big. But what happens when you go to part D? And alpha now is not 1%, but 10%. 4 was in the interval. Now, if it were the midpoint of the interval, I'd know it'd still be in there, but it's not. It's on the end over there. And you're going to go to 90% confidence, which means the interval is going to be smaller, narrower. And we don't know whether 4 is going to be in there or not. We won't be able to tell with without any more information. 4 may or may not be in the narrower 90% confidence interval. We knew that our p-value was more than 5%, but we don't know for sure if it's more than 10% or not. If I gave you one piece of information about this study, you would be able to, with some algebra, work out either the other confidence interval at 90%, so you could figure this last answer out. You would need to know the sample size. Because right now, without the sample size, you don't know what t-star would be, because you don't have the degrees of freedom. And you can't figure out then what part of that margin of error is the t-star part and the standard error part to work out the details. If I gave you n, it'd be a little bit of work, but you could actually recompute that confidence interval. All right, when you have a confidence interval already made, and then I turn to a hypothesis test, check to see if you can just make the decision quickly. That may be what we're asking you to do, rather than do a t-statistic, a p-value, and do all those steps. Helpful connection between the two. All right, here are your cookies of the day. This was sent to me by a student in the class. And so we have bar chart, we have a pie chart, we have some p-value. It should be what? P-values less than or equal to 0.05 up there. Yeah, got a Venn diagram. This crazy expression is your normal distribution model. It's the model for a standard normal density curve. There's your definition of A given B in a long way, and a QQ plot even. Quite a few things you should recognize there. There's a famous book, little tiny paperback book, doesn't cost very much, Lies, Damn Lies, and Statistics. Still a good read. And that 42% of all statistics are made up on the spot, they say. All right, there you go. They look pretty good. One last question before we're done. And a week off. Let's take a look at this. It's a good example. It's another question where you are given the confidence interval already computed. This is a confidence interval for the population mean expected salary. 95% interval goes from 83,000, some up to 84,000. Part A we have to work out. This was based on a large random sample of 1,000 students, and our confidence interval was computed. Part A asks us, can you give me the value of the sample mean? What was the average for the sample of 1,000 students? Where can we find that? That confidence interval was made with the following formula. They started with X bar. They went plus or minus some multiple of the standard error for X bar. So where is that sample mean in that interval? The middle. Just like your p hat was in the middle of your interval on exam 1 at 33% or whatever that was. So we need the midpoint, which means we need to add up the two numbers and divide by 2. One way to get it. I had some subtracting numbers and dividing by 2. When you get a midpoint, it better be a number in between those two bounds, right? Go back and check. We should have here about 84,250. 84,250. Include your units with a dollar sign. It's in dollars. That's the sample mean. And now you could also work out the margin of error. Whatever the distance is from that sample mean to an endpoint will be your margin of error. Next couple questions are true false. These are ones I'm going to have you click in on. We've done these ideas quite a bit. They can pertain to any interval we deal with now, whether it's about a mean or a proportion. So I'll give you about a minute to read those two questions, circle your two true false answers, and then we'll poll you. So you may click in on that first true false. If you're waiting for the rest, you can also take a look at part C. All right, let's have your answers in for this first one if you haven't yet. If repeated samples of 1,000 such students were obtained, we would expect 95% of the resulting intervals to contain the population mean. That is a very good statement. Indeed true. 90% getting it right. Why won't it let me pick? It's true. All right. That's a good statement of what? That is a good interpretation of the confidence level. Not the interval, because I didn't talk about the interval at all here. This is telling me what I mean by the confidence level. That's exactly what we mean. You have to identify the right parameter here at the end to say what you think will fall in 95% of those intervals. Good. How about the next one? You had a few of these like this on your homework 4 too? Quite a few. Beware of the word probability? Indeed, it should be false, everyone. Very good. What is that probability that the population mean is in between these two numbers? It's either 0 or 1. What's the probability that the sample mean is in between those two numbers? What was our sample mean? 84,250? It's in there. It's the midpoint, right? The sample mean will always be within that respective confidence interval. It will be the midpoint of that interval. All right? There's no probability really there either. It is in that middle. All right, this is false. This is not what the 95% confidence level means. But indeed, this range of values from 83,700 to 84,800 is a range of reasonable values. So how will you answer the hypothesis test in Part C? Trying to determine if the value of 76,100 is reasonable or not. What would you decide? Would you fail to reject, or can't tell? Now, is there something that is italicized there for you? Underlined even here? So the answer is reject H naught. But would your explanation be enough? Is the explanation of 76,100 is not in our interval? That's not quite enough. It's true, it's not in that interval, but that interval was a 95% confidence interval. And I'm actually asking you to do the test at a 10% level, which means you have to imagine the 90% confidence interval, which we know would be narrower. So your explanation needs to be that 76,100 would not be in the narrower 90% confidence interval. It's not in the 95%, and therefore it won't be in that narrower one either. And one last question of the day, looking at that QQ plot. Go ahead and read it. We know there are two conditions for the interval or the test to be valid. Those two conditions, one is about the sample. The sample needs to be a random sample. We'll assume that holds by how they gather the data. The other is that the response for the population needs to be normally distributed. To check that the population model's normal, I'll make a graph of my sample, which will at least reflect what I think is happening in the population. And one good graph is this QQ plot. The QQ plot here shows some departure from that straight line reference, where the points should fall if they were really truly from a normal curve. Is this cause for concern? Would this mean that our confidence interval in the test that we just did in parts A, B, and C are not valid? Or do we get a free pass? Do we have something that's working for us that allows us to still do that confidence interval and still do that hypothesis test, even though the condition of the population model being normal does not seem to be met? What did we do? We took a sample of 1,000, which is large. Is this cause for concern? No. The sample size is large. Now I'm going to have you listen for another 30 seconds, because most students will still say something wrong after this. The sample size, n of 1,000, is large. It's large enough to invoke what famous result? The central limit theorem, which does what? Here's what students think, and it has to do with your good, true, false on your homework 5. Students think that if you take a large enough sample from your population, it's going to make that population look more normal, just because you took more data from it. It doesn't make the population of salaries look more normal. But you took a large enough sample out of it, 1,000, and you calculated an X bar, and the model for X bar will be approximately normal. When you did the applet in labs, the top graph, your population model up there, never changed. But when you took samples of 25 from there, what happened to the model for X bar down here? It always tended to look approximately normal. Students think that taking a large sample size makes the original population look more normal. It does not. It makes the model for X bar be approximately normal, and that's the thing you're standardizing. That's the thing you're using in your confidence interval. That's what needs to be approximately normal. So it will make what? The central limit theorem, which will make X bar be approximately normal. And that's what we need to do the test and confidence interval. All right, I do wish you a very good break.